Okay.
Welcome to a new lecture in our computer vision class. So far, we are familiar with some traditional computer vision technique, including image enhancement, key points finding using corner technique or plots technique, extracting edges, line detection, feature detection using either theft, surf, multi-scale technique. So we now have good understanding of how we can use traditional computer vision technique that used to be used until, let's say, 2016. Okay. Are those techniques still in use? The answer is yes, you are using them, and you are using them a lot in several applications. But since then, or to be more accurate, since 2012, there is a big jump has occurred. This big jump was the development of high-end, low-cost graphical processing unit, the GPUs. Okay. By that time, we could do many sophisticated high-end computation or small-scale graphic cards that can cost less than $500 to $1,000 that we used to do on machines with 20, 40,000. That's why people start to make a shift and interest. Instead of using the traditional technique for feature finding and points of interest and feature matching and all of this traditional technique, they said, why don't we go to another technique, which is what? Which is using the statistics. Can we use statistical method to find some information about the images or find some feature or some useful information inside our images? So on this approach, they switched to some part in computer science called machine learning techniques. To understand this, let's go through some understanding to some insights to understand the difference between the machine learning and all other types of AI, including whatever we are covering here, which is the computer vision. Actually, when you hear the word AI, what comes to your brain? I asked you, what is AI? What comes to your brain?
Something generating.
Okay. I ask you, what's AI? What will come to your brain?
Automating everything.
Process.
Make a model act like a human.
Okay.
Something like ChatGPT, which learns by itself based on data.
Okay.
The ability of the computer to make decisions. So,
Okay. So the word AI actually is a big expression. It's the way we are trying to simulate or emulate or build something that do the same thing that our human brain is doing. So we have natural intelligence that we have in our brains, and we are trying to move or copy this natural intelligence into machines. That's why it's called artificial, which again is the natural. Okay? At the beginning, they said, let's try to make this AI more specific by track, by application. Meaning, I want to design or emulate the part in our brain that's responsible of hearing. Okay? So they went to the ears and find the way it's working, how it's connected to the brain, and based on that, they're trying to generate parts of AI that do or simulate the same action. So they found substrate transform using the Fourier, the wavelet, all those techniques. This is considered to be part of AI, but it's called narrow AI because it's trying to solve one specific problem. And in this case, I don't have that. I'm trying to design technique that simulate the human intelligence. So the way the human is hearing, I'm trying to simulate it with machine. Do I have any data involved in the problem? The answer is no, no data. I see here, for example, the ear horn, so I can make horn, then drum, something like the drum, and so on. Same for the vision. For the vision, I'm having the pupil, the lens, so I'm trying to design similar technique to capture the image. So we design the camera and all what we covered so far. That's why we are calling this narrow AI, something that's work to solve specific problem without having data. We are just analyzing the natural model, and from this natural model, we are trying to come up to artificial version. And that's what we have so far, right? When we discuss the point of, or the problem of matching, the problem of feature extraction, all these problems, by just trying to find how the humans define the problem. Like if we say, what is the corner? The corner is the way when we shift this or this or this, we find change. So we defining what exactly the item we are looking for, then we convert this into mathematical equation to solve it. Same thing we can do for the speech, same thing we can do for robotics, for planning, for natural language processing, for anything. So we don't have any data. We are working on, we have human model or natural model that do the task, and you are trying to do something similar, artificial. And the limitation behind all of this, that we don't have enough computational power. Okay, we had regular machines, traditional processing units. By 2012, the GPU start to be in action for affordable price and good computational power. That's why people start to follow a specific path called machine learning technique. What is the machine learning technique? Machine learning technique is a branch of the AI where you are not trying to follow the features or the problem specification step by step. No, you are just getting samples. So machine learning rely on learning by samples. How? Like their motivation in this concept come from kids. When you teach a kid how to eat, do you give him instruction? First, hold the fork with your hand, then put the fork in your food, then catch the food, then put it in your mouth. If that's how you are doing? No, you are giving him a role model. You sit next to him, use the fork, do this, put this, the kid will do what? Similar action. So learning by samples. Giving the kid example, and the kid will follow the same example. This is the main idea of the machine learning. So we are trying to collect as much examples as we can that solve or concerned with a specific problem. Then we are trying to build a model, and this model should be able to learn from those samples. So the machine learning technique basically comes from statistics. It's a mathematical technique. It's not engineering technique more than mathematics. Okay? So we are trying to collect several data that follow some statistical distribution, and from this data we are trying to build mathematical model to understand the hidden insights between those data. Okay? What are the techniques we can use for machine learning? Actually, a lot. There are something called supervised learning. Meaning, when I give you the example, I will give you the sample and its solution. So I will give you X and Y. Meaning, if I give you photo for a person, I'll tell you this is Mike. Okay? And we will give you another photo for Bert, another one for Julie. So all the images I have are marked. So I have the sample and the label for this sample. So this is X and this is Y. In this case, I have the sample and the label for the sample. I can use this label to supervise the learning process. That's why it's called supervised learning. What are the techniques used in the supervised learning? There are lots of techniques. There is support vector machine. There is linear regression. There is decision tree, random forest. So many. All of those considered to be supervised. We are not concerned about all of those. Okay? Because not all of them used mainly now in machine learning. Yes, we still use some of them, but not that much. Another technique called unsupervised technique. What is the unsupervised? In this case, I'm giving you only X. There is no Y. Meaning, I'm giving you several pictures, but I'm not telling you which picture for who. Just giving you the picture. Then what I will do with those pictures? Actually, we can use also statistical technique to analyze those pictures without supervision. Like what? There is some techniques called dimension reduction technique, including principal component analysis, linear discriminant analysis, independent component analysis. All of those, actually linear discriminant is part of the supervised, basically. Principal component, independent component, and many others, KNN, K-nearest neighborhood, all of those considered to be unsupervised because I can use those techniques to reduce the dimension of my data and at the same time try to find internal characteristic between the data. What does this mean? Assume that I'm having an image of size 100 by 100. In this image, I have a face for someone. Now, does the face use all the area of the 100 by 100? No. If you check the face pixels, you will see that the number of pixels used by the face may be 50 by 50. Okay? And inside here we have also some area that's considered to be extra. Now, does it make sense that I use this model for detection or for recognition or for features? They said no. They said, I can reduce or first convert this into a vector. This vector will be of the dimension of 10,000 by 1. So each pixel here will be converted to a point in the vector. So I will start by this row, put them here, the next row here, here, and so on. So it will be 10,000 by 1. Then, using the principal component analysis technique as an example, I can reduce this vector into only 500. So this 10,000 will go to only 500. And those 500 will be well representing the data here as much as we can. So the most important components inside here will be converted to this 500 components. Okay? Actually, there is a lecture about the principal component analysis available on campus for you to watch, okay? Which included in the midterm. Okay? That's why we are calling this unsupervised technique. Again, it comes from statistics. Some people can have data, but this data is mixed between supervised and unsupervised. Some images are labeled, some are not. Initially, they said, I can't mix both of them. I need to work with the supervised as supervised and with the unsupervised technique. Later, they said, why not? We can use whatever we learned from the supervised to help us improve the quality of the unsupervised. And based on that, they came up with another technique called semi-supervised. So semi-supervised technique is a machine learning technique that deals with data that mix together. Supervised with unsupervised. Some scientists say, that's good. What we have in here is extremely good. But assume that I want to learn the kid how to walk. 1-year-old kid or 6 months. If you provide him with supervised example, he sees exactly how you are walking, right? So he can see that. How he can walk by himself in this case? If you look to the baby, when he's trying to walk, you will see that first, he will try to stand up, hold something, then support his action by holding this object. Then move away and try to walk by himself. If he succeeds in the first step of standing up, he will continue. If he didn't success, what will happen? He will fall down. Then he will try again. Fall down again. Then we'll try again. So he will keep trying to do the same action again and again until his bones adjust itself to the correct position where he can stand stable. Right? So he is doing action, and based on that, the environment itself reward him or punish him. Reward by giving him stable action, or punish him by falling. So that they came up to the concept of reinforcement learning. So the concept of reinforcement learning, simply, you are having agent or model that doesn't know what to do. He will try to interact with the environment, trying to do some action, so that the environment will reply with a comment. This comment can be positive, reward, or punishment. So it can be positive or negative. The model should use this reward or punishment to adjust itself and try again to do the same action. Then you will get the feedback again from the warrant and adjust itself again and keep doing this again and again and again until it can do the action correctly. As an example, because this is used a lot in robotics, assume that I have a robot right now standing in this position and the robot wants to go to the door. The robot doesn't know the environment. How can the robot react? The concept or the basic reaction is random reaction, right? It will keep going straight. So the robot will start to go straight this way. It will hit this wall. So he will not react that continuing this way, he will see a wall. So he will go to the initial position again. This is the safe position. He didn't face any problem here. Then it will try to rotate a little bit. Do the same action again. Hit another wall. Go to the safe position. Adjust the angle a little bit. Go straight. Hit another wall. Go to the safest position that he knows, which was here right now, because now he left his original place. He will adjust his position. Go straight. He will keep going until hitting the wall. So now he will know that this position is safe. He will stay here. Then try to find a safe angle. Do the same thing until it finds the door. So learning by trial and mistakes and doing correctly, this is the main concept of the reinforcement learning. And this is actually the main concept used now in the modern LLM model, especially the DeepSeek. Did you hear about the DeepSeek? The DeepSeek model learned by the reinforcement. It's not supervised, it's not unsupervised. It tried to mix the technique, but basically rely on the reinforcement technique. Okay? All the other chatbots still use the reinforcement in the background. So, as an example, assume that, which happens a lot actually, assume that you ask the ChatGPT, how many are in the word strawberry? I think I told you this problem in the beginning, the beginning of the semester. In many cases, it's saying 2. Sometimes it's say 1. Sometimes it's say 3. Assume it's say 2. What will be your action? You will tell that this answer is not correct. So this is your feedback. This is the punishment. Negative rewards that you are giving it. So the chatbot will use this negative feedback to adjust itself to avoid this problem again. Of course, it will not do this in real time. With ChatGPT, it will take long time to do it because you should take permission from the training company to do that. But with DeepSeek, is doing it in real time. Try to adjust the or check if the answer is successful that you said. Then based on that, it will adjust itself. Okay. Anyway, now again, technique. They are not new. They are old. Some of them from the 50s. Okay? The new thing is, again, this. The computational power. This is the new thing. That's why people now think about, or thought then, about simulating the human brain, literally. How the human brain is working. So they said, to achieve the same performance of the human brain, I will build a human brain. How? by building neurons, exactly similar to what we have inside the brain. And based on that, they came up to another technique which called deep learning. So deep learning is a subset of the machine learning technique, which is subset of the artificial intelligence. There is a specific problem that the deep learning work on, not the others. The answer is no. The deep learning can work to solve any of those problems. It can work for the vision. It can work for the robotics. It can work for the speech, for the natural language, for expert system, for planning, for anything. So deep learning considered to be a tool as a part of the machine learning that we can use to solve any problem if we have data. So the condition to use machine learning and of course the deep learning, that you need to have samples, data. If no data, no machine learning. No data, no deep learning. That's why nowadays data is money. That's why companies now sell your information to another people, because they need your data. They will use it to train their models. Okay? So without data, no models, no learning. Okay? Now, can we have one model that solves all of those problems together? Still not yet. But if we have that, we will call it artificial general intelligence, or AGI. I'm not sure if you heard this word before, but start to be available a lot these days. So if we have one model that solves all of those problems simultaneously, we are calling it artificial general intelligence, because now it's doing the same action that we are doing as human. You have one brain that can drive, can hear, can visualize, can control your legs, can control your arms, can do everything with one model here. Now, if this one can do everything like this, then we have a general intelligence, right? Okay, is this clear? Okay. Now, as I said, we used to use all of this traditional machine learning technique for a long time, until we had the computational power of the GPU, which gave us the chance to move or shift from this one to the deep learning. Because deep learning, as we stated, it's simulating the human brain, what's going inside here. The other advantage of the deep learning is it's end-to-end. What does this mean? In this traditional technique, any one of those techniques, we have to start with the image. Assume we are working with faces. Then we are trying to extract features. Those features can be the eye locations, nose locations, the face borders, mouth, all of these things. Then those features, or we can extract the histogram of gradient around all those areas, converting them into big vector. This big vector can be of 1 million samples that represent all the components that I have here. And based on that, I will start the recognition process by matching this using the other, using the same technique we use with the ROC, or by applying support vector machine, or any technique you would like. The good thing about the deep learning is you don't need to do that. You have the deep learning model, and the input will be this image. and the output is the class or the label. You don't have to find any feature or do anything. All the magic will happen inside here. You apply the input image, and you have the label on the outside, and everything will happen here without touching anything. So any feature you think it can be useful, it will be extracted inside. That's exactly what we want to understand here. What type of magic that occur inside this deep learning model? Okay? To understand this, let's start to understand the challenges we have in those problems. So this is a simple image for a cat. In this case, we are trying to solve a problem. We are calling it classification problem. What all of this means? It means that I have image that include objects. And inside this image, I'm trying to say what type of object included. Does this image include cat or bird or deer or dog or truck? According to that, the correct class is cat. That's based on our intuition as human. Now, we want to design a model here in between. It will take this image as an input and give me which one of these correct class. Now, start with the dimension. What is the input dimension for this model? As we stated before when we started the course, we said that we have two types of image, right? Grayscale and color. If the image is grayscale, how we are describing it? How do we describe the grayscale image? By n, which is number of rows and number of columns we have in the image, right? If it's a color, in this case, we will have three layers. Each one of them is m by n, so it ends up to be m by n by 3. This is m by n only. So the input that will be applied to the model will be the image either as a grayscale or as a color, direct. What will be the output? In this case, the output must be all possible classes we can achieve from this data set. Meaning, for this data set, I have images for cats, for birds, for deer, for dogs, for trucks. So this model will have 1, 2, 3, 4, 5. I have 5 outputs. So number of outputs must equal number of classes. Okay? Now, each pixel here is represented using a number from 0 to 0 to what?
255.
0 to 55. The output here will be what? It should be indication to the class, right? But what? What exactly should be the output? They said the output must be the probability that this image belongs to this class. Statistically speaking, we want to find the probability of y given x. The probability that this class, which is y, is correct if I see this X. So the data I'm receiving here is nothing but a probability distribution. Meaning, if this is a cat, the value here at the cat should be about 0.9. Maybe detected as a bird with 0.01. Sorry, yes, 0.1. Detected as a deer, 0.01. Here, 0.01. And here is the rest, let's say, as a truck, okay? So 0.07. So the sum of all of this should be what? It's a BDF probability. So the sum of all of those must equal 1. Based on that, I will find which one of them had the maximum probability, the highest probability, which is in these cases the cat class. Okay? So in the classification problem in general, the input will be plain image, either as a grayscale or color, and the output will be the probability that this image belong to those classes. Okay? It's the only problem we can solve using this model. The answer is no. There is another type of problem called regression problem. What is the regression problem? This said, in this classification problem, the output here is discrete category. So I have categories here, and my goal is to find the probability of each category. So it's a discrete category. In the regression problem, the output is continuous. What does this mean? Assume that you are working over time and you are measuring the stock price for some company. So if you check this, you'll find that the stock value is going up, then maybe going down, then go up again, then down again, then jump, then manage. So it will be look like this. So if you look at any time point, for every time point, there is a value for the Y. So the value of Y is not broke over any time point. Also, if you check the value of the Y here, you'll find that it's continuous. It's not discrete by any chance. So this is continuous, and this is continuous. The domain and range, both of them are continuous. That's what we call a regression problem. So for the regression problem, the input is continuous, the output is continuous. For the classification problem, input can be continuous, but the output will be discrete categories. Okay? Now, I'll start with the first problem, which is the classification. So the image, as I said, I can describe it. If it's a color, to have number of rows, number of columns by 3. And each pixel value go from 2 to 255. Now, what is the challenge for this image to be used with any of other techniques? Any one of those? The answer is, assume that if you are working with this, I don't have any challenge. The cat is taking almost all the picture. I have all the features of the cat, eyes, ears, skin, everything. I can see from all perspectives that this is a cat, okay? But what if I have many cats. And each of them has a different color, different age. What if I have different type of cat, subcategories? So this cat, different from this, different from this. Each one of them are subcategories from the main category, which is the cat. How about if I'm having a camouflaging? If you think about the traditional technique of the machine learning, or sorry, the computer vision, what we learned so far, can we find, for example, Sift over this and match it with the traditional cat? Will it match? Do you think? This with this. Because this is the image that we have for the cat, right? And this is the query image. I'm asking you to search for the object in it. Can you find the cat here using this technique? It will be lots of challenge. Here also, same thing, as you can see. Do you see the border of the cat actually? Somehow here. Okay. How about this? Illumination issue. So if it's dark, semi-dark, full light, and the shadow. So if you look like to this one, you will see it's a cat or you will see it's a tiger. For me, it looks like a tiger more than a cat, but it's a cat. Okay. Deformation, which is one of the biggest challenge we are facing in the computer vision problem. If you have object and this object can change, okay? Here, this cat can have this position, can be this position, can be in this position, can be in this position. So traditional methods can't find the cat in this case. And of course, the occlusion. You see? There is a cat here, but the only thing I can see, the hand and the tail. Here, it's fully covered with the grass or whatever this one part is. And here is with the covered with this blanket. Okay? So if we decided to use the traditional method technique, we will start by having samples. Then from those samples, we will divide them into two categories. First category, we are calling them training. Those training will be used to train our model and make sure it see or it could be able to extract the useful information from those samples. Then, after training our model, we will apply something to it called testing. So training used to find the parameters of our models. Testing used to test the performance of those parameters under new unseen data. So those testing set or testing data must be completely new, something that the model didn't see before. So those must be separated from those, completely separated. Those will be used to train this model. When I say training, means finding the internal parameters of the model, and we'll come to this in a second. Then this will be used after training to test the performance. Is it working well? Is it not? As an example, assume that you have stock market example, and you have the data until what's today date? 24. So 3/24. 2025. Okay? And you trained your model based on this pattern. So those become the training sets. Now, you run your model to expect the data for tomorrow, which was this segment. So here, this segment is for tomorrow. You will get the data you extracted from the model, compare it with this unseen data, and based on that, we will match if the generated data is correctly detecting or expecting the next day or no. Another example. Assume that I'm training a classification model. So I will use those samples to train my model. Then I will test it on those subsamples to see if it will be able to detect it or not. Okay, so any data that you have to train your model must be divided to at least those two groups. But for training, that can be used to find the parameters of your model, and testing that can be used to analyze and understand the performance of this trend model. Okay? My data or my problem is supervised. In this case, both the training and testing will have inputs and labels. So this is X and this is Y. My model is unsupervised. This, in this case, I have this only, I don't have this. For testing, I'm applying the input data. Then I will compare the extracted Y, which I will call Y bar, compared to the actual Y. So I will compare this to this to see the performance. Okay? Now, in the traditional learning, to do this supervised technique, we get the input image, then extract features from this image. Those features can be SEFT, SURF, ORP, multi-scale, whatever the type of feature we are using. Okay? Then we either try to use the machine learning techniques, traditional like support vector machine, decision tree, random forest, or whatever technique from the machine learning on those features, or we can handcraft the algorithm by ourselves, as we did for the corner detection or line detection or whatever the technique we use. Then we can check with the output to find the match, or we can use the deep learning technique. Deep learning, as I said, you have the input image and the output prediction, and inside here, the magic happens. The features are detected automatically, and the model that do the classification also learn it automatically to learn that this input belongs to this class. When I get this, I should produce this without any design, external design from your side. Okay? So this and this, the only thing that need to be applied to our model. Okay? Now, let's take this deep learning and deep understanding. So when they start to work with the deep learning, they thought about the human brain. What exactly our human brain, or how our human brain works? They found that Human brain consists of neurons. This is one simple neuron. The brain consists of several neurons connected together in parallel and in cascade. Meaning, I have neuron connected to the second, then this one connected to the next, and this one come from here, this one connected to this one connected to this, and follow. So I have a big network of them. What if the neuron consists of? They said it consists of synapse. Then we have axon. Actually, let's spell this first. Axon. Then presynaptic terminals. And we have here dendrite. And this is the cell body. So this is the cell, this is the axon, this is the synapses, this is the presynaptic terminal. Those synapses receive the signal from the previous stage, then process them inside the cell body and produce some signal or output to the axon that can be sent to the next stage. Now, what type of signal happen inside this neuron? Is it electric signal? Is it mechanical signal? Is it what? Electric. Actually, it's chemical. It's electrical. Okay? So, we are now trying to simulate something that happened in the body using chemical reaction, externally using external voltage. Can we do this? They said yes. We will build this thing. What is this? This is called perceptron. Its part will simulate the axon that we have here. Sorry, the synapses that we have here. So each one of those receive input. Then I will multiply this input to a weight. This weight is giving priority for this input. So if some signal coming from the heart should have a high priority from the signal coming from the finger, because if the heart stops, what will happen? You will die. If your finger is bleeding, you'll die. There's a signal coming from here and signal coming from here. But this one has low priority than the signal coming from the heart. So the weights here will give priority to the signal, depend on the source who sent it. Those weights are our trainable parameters. For the young kids, those weights are tuned with time to give priority to parts of the body or parts of the peripheral over the other. So those are our trainable parameters. The parameter that we are looking to adjust or to modify in the training process. Then, all those signals that multiplies to the weight will be added together. This, plus this, plus this, plus this, plus all the others. With some bias. This bias comes from the internal characteristic of the neuron. Like sometimes you hear that someone has high electricity in his brain, right? So this means the bias is high a little bit. Okay? After that, if the value of the signal arrives to specific threshold, we will start to fire to the next step. So, as here, if the signal string is higher than a specific threshold, it will start to fire to the next neuron. Same here, same here. So I need to have some thresholding function. If this signal over this specific threshold, it will fire to the next neuron. We will call this function for the firing as an activation function. Okay? And this, as we call it piles. And those W's, we call them weights. Okay? Now, as I said, this model considered to be a simplest model that simulate the biological neuron. And they are calling it perceptron. This one was found in the 50s by a psychiatric, not computer science, not mathematician, psychiatric who found this model. Okay? Let's now simplify this model. This model, as we said, has an activation function, has a bias, has so many components in it. We want to simplify it. We want to make it linear. What is the condition for linearity, if you recall? There are two conditions for the function or the model to be linear. Can you remember it? Or can you remember them? The midterm is next week, right?
Is it for transformations? It's the one I'm continuous.
Two conditions for the function to be linear. To have f of x plus y equal f of x plus f of y. And if you have f of ax, this is equal a f of x. If any function that satisfy those two conditions, the function means it to be a linear function. Now, does this model a linear model? With this view, it's not. So we'll try to simplify it to be a linear model. So we'll start by an image, let's say of a size 32 by 32 by 3. Very small, simple color image that we'll use as an input. Now, if we convert this into one vector, what will be the size of this vector? They said every pixel here will be converted to part in this vector. This means 32 times 32 times 3 will be converted to 3072 by 1 vector. So this is my input. Then I will define a linear function between this x, which is this image, and the weights that I'm training inside. I'll call it W. This linear function should produce y, which is the label. As we stated, for simplicity, we will consider that we have 10 classes. So if we want to apply this mathematically, the model will look like this. First, this one, as I said, is 3072 by 1. It will be multiplied times W, which is 10 by 3072. This is a matrix multiplication. So this one equal this one, they will cancel each other. So the result will be 10 by 1, which is my y. The scores of those 10 classes. Now, this problem is linear or no? Yes or no? And this a linear model or no? Yes, it is. This is exactly similar to having f of x equal ax, which is line path through the origin like this. It's a linear model. It has no problem with that. Okay? Now, if you look here, we are now simulating this part. Because we are doing matrix multiplication between W and X. But the equation here has another part, which is what? B. We add this B or no? Answer is yes, I can add B. But if you did so, the model will not be linear anymore. So the equation, this is not a linear equation, even though it's an equation for a line. But because this, it's shifted from the origin. So if you apply the concept of f of x plus y, you will find that it's not equal f of x plus f of y. So this is not linear. Okay? This is a linear model. This is not a linear model. Now, can we convert this non-linear model to a linear one? They said, yes, I can do this trick. How? Let's focus on this part. For simplicity, we will reduce the size of the image into only 4 pixels. Very simple example. First, we will convert this into a vector. So it will be vector 4 by 1. Again, as I said, I'm converting the row into column. Row to column. So become vector like this. According to this definition, I have to have the number of classes. Again, for simplicity, I will consider 3 classes only. Cat, dog, sheep. Based on what we have so far, the W here, if this is 4 by 1, this will be 3 by 4. Right? And B should be 3 by 1. I will start by any guess for W. Any guess. And any guess for B. Okay? So this is the 3 by 4 value for W, and this is X. I add it to B, then I'm generating and having this Y. It said, let's make this small trick. What is this trick? I will move this one from here and concatenate it to this W. Can I do that? Can I move this one from here and concatenate it here to be part of the W? So this will be, ignore this, and this will be 3 by 5 and multiply it with 4 by 1. Can I?
Yeah. Actually, I'm not sure.
No,
You can't. Because the dimension mismatch. This one should match with this. This is matrix multiplication, right? So I can do this trick. But I can do it with one condition. If I add extra element. So this one will be 5 by 1. And we can do this. So I'm moving the B to be part of the W, and I'm increasing this element to be 5 by 1. In this case, the equation will become what? This is 3 by 5, and this is 5 by 1. So voila, we return back to a linear equation. Okay? So now I can consider this problem or this model, simple model, a linear model. But with this trick that I did. So the piles will be considered always part of the W. Means that the bias is trainable as well. So when we are training the model of any neural system, we are training the weights and the bias. Okay? Because the bias is considered to be part of the weight system. Okay? So now I'm training that to be multiplied by my input to produce vector. This vector should be the probability that this image belongs to this class. So this value should be the probability that x, y given x, the probability that the cat belong to the cat class, or to, what is the other class that we stated? Dog or sheep. So this is dog, cat, dog, sheep. Okay? So now I converted the model back to be a linear model, okay? By having the bias to be part of my W, okay? So, does this affect me a lot? The answer is no. Because if the model is linear and I have any change or scaled version from the input, all what happened that I will have a scaled version from the score. So if I change the illumination of the image by half, the value of the score will be reduced by half. Reduce here, increase here, increase here. So this one is a scaled version of that. Okay? Now, we are calling this model an algebraic representation. This is a simple perceptron model, and this is the algebraic representation of the model. By having the input multiplied as a matrix multiplication or inner product. You can find it, we can read these two expressions in the books. Matrix multiplication or inner product. Between the input and the weights, this will produce the score for the classes. Is this the only representation for this model? He said no. There is two more representations. What is the second one? To see the second one, they said, let's rearrange those W's. If you look at the W in the first row, it shares the same exact dimension as the image. 4 by 1, 4 by 1. The second one, 4 by 1 as well. The third one, 4 by 1 as well. Let's reshape those to look similar to the shape of the image, which is 2 by 2. So if you reshape this to look like the image 2 by 2, reshape this to look like the image 2 by 2, reshape this to look like the image 2 by 2, it can give us other hint about what are those weights. To be more understandable, we will try this on large number of samples like those. And we'll see what are those W's after we reshape them to look like the image, they will look like. And we figure out those shapes. Those weights, after we reshape them, we found that they look like a template for the class. So the weights for the plane class look like a plane. This look like a car. This looks like a bird. This looks like a cat. This looks like a deer, like a dog, like a frog, like a horse, like a ship, like a truck. So the weights of this perceptron model can be considered or be interpreted as a template for the class we are looking for. This is a good point of view, but is this a good way to build a classifier? They said not really. Why? Let's look to the horse. Where's the horse? Here. If you look here, you will find in this image, some horses are looking to the right. Some others looking to the left. Some in the middle. Now, if you look to the template, can you tell me this horse in the templates is looking to the left or to the right?
Middle.
Looks like both.
Exactly. That's two heads. One in this direction and the other in this direction. This means that those templates are not enough to represent or to understand the given data. Yes, they are templates that represent the internal characteristic or the internal behavior of the data, but this simple representation, which is one pattern per class, is not enough, because the class can have several representations. Here as an example for the frog, some frogs are green, some are brown. If you look to the frog here, do you see the green? Sorry, this is the frog. Do you see the brown? Mostly for what? Green, green, green. The brown frog is not showing that much. Okay? So using the linear classifier or linear perceptron model is not suitable or is not a good technique if the data that I'm having or I want to work with having multi-representation. Okay? Any questions so far? Now I have two representations for this linear classifier. The first one is an algebraic by having a linear equation between the weights and the inputs. The second one, considering rearranging the weight, we figured out that those weights are templates, patterns for our data. Are those the two only representation? No, we have one more. To understand the third one, they said, let's start with one pixel only from the image. So this image has 3072 pixels. I will choose only one. For this one pixel, I will calculate the score, classification score for those three classes. The car, the deer, and the airplane. Again, I have here 10 classes, not the only 3. By the way, the data you're seeing here is from data set called Cipher10 dataset, okay? Which is very well-known dataset, and you will use it in one of the homeworks, okay? The dimension of the data here is 32 by 32 by 3. All of them are colored, and the number of classes here is 10. That's why it's called Cipher10, okay? So for this data set, I'm using only one pixel. And for this pixel, this will be 1 by 1. So the W here will be 3 by 1. And this will be 3 by 1. And it will generate the score here, which is 3 by 1. Then I will plot the value of the score for all possible value for the pixel. The pixel can have value from what? 0 to 255. So for the value of 0, the scores with that. The value of 1 scores with that, and so on. Then I will connect those scores. Now I will make it more advanced. I will take one more pixel. In this case, X will be 2 by 1. In this case, W will be what? This is 2 by 1. This will be what? 3 by 2. In this case, this will be 3 by 1. So the result here will be 3 by 1. And each value of those pixels will have a different axis. So we have axis here and we have axis here. Now again, for this pixel, go from 0 to 255, from 0 to 255. And I'll calculate the score for the car, for the airplane, for the deer. I'll find that I'm having lines. If you check those lines, you will see that all the car value belong up to this line. So the score must be higher than this line. If you look to all the images for the airplanes, the score will be higher than this line. If you look to the scores for deers, the score will be higher than this line, which means that this area will be the area for the scores of the car. This area will be the area for the scores of the airplane. This area will be the area of the scores of the deers. Okay? This means that those lines are a separator, are barriers that separate the scores of each class from the others. And this is the third representation for the linear classifier, which we are calling it geometric representation. So those W's are nothing but a hyperplane. Plane or a separator that separate the scores of each class from the others. Here, I'm having 2 features, that's why it's a line. If you have 3 features, it will be a physical 3D plane. If you have 4 features, it will be 4-dimension plane. If you have 3,000 features, it will be 3,000-dimension plane. That's why it's called a hyperplane, which means it's a plane, but in the higher dimension. Okay? So this representation is very important because it can give us indication if the linear classifier can solve a problem or no. Because linear classifier will generate what? Line separator. So if I have problem like this, two features like this, those are the samples. For class 1, those are samples. For class 2, and I want to design classifier that classify them, I can easily separate them with a plan, right? One line that separates those and those, do the job. So linear classifier can separate those two features. But how about those? Here we have samples here for class 1. And samples here for class 2. Can you find one line that separates those from each other? Never. You can't. How about these? Samples for class 1 here. Sample for class 2 here. Can you find one line that separates them from each other? Again, the answer is no. Same here. There is no one line that can separate them from each other. So each representation for the classifier has a different meaning. First one is just a linear equation, which is matrix multiplication or inner products. The second one is a pattern, is a template. Why the template is important? So this one is important for the separation. Why the template is important? Actually, the template concept used to be a valid concept for matching for a long time, using something called normalized cross correlation. And this technique is still used until the moment in industrial application, where I'm having, for example, computer board or electronic board that has specific chips. Okay? And I want to do an inspection on this board to see if the chip is existing or it's missing. So I'll start by a pattern or template for this chip. Then I will do search using normalized cross correlation in my board to highlight the place of this chip in the board. If I found them in some specific locations, then passed. Board is correctly having the components. If I didn't find them in the location, fail. Put them aside. Okay? So the concept of template search or pattern search is very important in many applications. Okay? That's why the linear classifier actually doing a kind of template match in this case. Okay? So, in a conclusion, I can say that any linear classifier can be represented either as an algebraic equation or in a visual representation as a template. The weights, of course, can be interpreted as templates, or it can be considered as separator, some hyperplan that separate the space between our classes. But if this technique sufficient enough to solve sophisticated problem, the answer is no. Because we saw this example, it fails to solve it. Okay? And there are so many other examples. Okay? So we need some advanced technique to solve those problems. But we handle some problem right now, which is what? How can we find those W's or those templates or those hyperplanes? Now, I know the model. The model looks like this. I know X is given. And the expected value of F, which is Y, also given. Now I want to find the value of W. How can I do that? For this purpose, we will start to do a kind of searching problem. Something we can use to find suitable value of W that can be multiplied times those image to produce the best score for those classes. We can do this actually using something called loss function. What is the loss function? Loss function is nothing but an optimization problem. some function, which is function of W. If I change the value of W, this value function will change. My goal is to find the minimum value for this function and the associated W that give me this minimum value. Meaning, this function must be, if possible, something like this, concave up. If the value here is minimum, this minimum value, I will check the value W at this minimum value, and this will be the best W that can solve this problem for me. And this W will be the optimized solution to the problem. So this loss function must satisfy some conditions. First, low loss means the classifier is good. High loss, the classifier is bad. When I say low loss, the best loss value is 0. Meaning you can't have negative value. So the loss function cannot be negative. Never. Loss function must produce positive value all the time. The best value for it should be 0. It can be bigger than that. But if I achieve the 0 loss, this is the best solution you can have. In some books, you will find it called objective function, cost function. Sometimes they are calling it reward function, profit function, fitness function, utility function. Call it however you would like. Depends on the way we are solving or we writing it, or your background especially. So if you are coming from business background, you may call it profit function or utility function. If you are coming from mathematical background, you will call it fitness function or objective function or cost function. If you are coming from engineering, we are calling it loss function. So depending on your background, you will have the name for it. Okay. So you are receiving negative value for it. In this case, the problem converts to maximizing rather than minimizing. Okay, which is not something we will handle actually in this case. And this one, this name, which is the reward function, one of the names we always use with the reinforcement learning, if you recall. Because we apply the action and we receive the reward. Okay? So some people relate it to this part. But again, this is not something that we will handle in this course. So we will start or we will test this loss function over all given samples. So those are samples or examples. Those examples are supervised, meaning I have the data and the label. How many samples I have? N. This N can be 10, can be 100, can be 1,000, can be what it is. Okay? Depend on the amount of data that you have. So this X is my image. This Y is an integer, which is the label. Usually, this X is the image, and this Y is a vector that has 1 in the correct class value. So assuming this image for a cat, the position here of the cat will be 1, all the other positions will be 0. Okay? Sometimes we are, instead of having it a vector like this, we are saying 0, 1, 2, and here we have 2. So either way, this representation is okay, this representation is okay. This representation is the actual one we are using for the training. Why? Because this is a PDF. All the value here are 0 except this is 1. So it satisfies the condition of the probability. Values are positive, the sum of all values are 1, and the maximum value is 1. So all the conditions for the PDF satisfy for this vector. That's why we are using this representation. For as a shortcut, we can represent this with the number. So this indicates the position. Okay? But for the actual training, we are using this representation. Now, for each sample in this data set, I will evaluate the loss function by applying the X to the classifier and produce the score. Then the loss function will compare this value or this vector with the scores coming from this classifier. Based on this comparison, I will produce the score for this sample. Then I will apply the next sample, and I will add those together to produce my final loss function. So the total loss is the sum or the average of all losses for all samples over the number of samples. So this is average loss. Okay? So that's the concept we will apply. Each sample applied to the classifier, produce score. This score will be compared to the original score, produce loss value, sum those over all the samples, and find the average. Now, what is the best loss function can be used for the classification problem? Actually, we have several types of loss function can be used, but there are two most common loss functions. The first one is called support vector machine loss, or Hing loss. Either this or this. This function say what? Said that I will generate the score for a specific sample. So I'm calculating Li, F, Xi, and W. So this is the score. Then I will compare this score with the current score for this sample and compare it with the score of the other classes. Then try to give margin of error and try to push the actual score far from this margin. Then, if the result is 0, this means I'm having a good value. If the result is not 0, this means I need to tune the W again. Meaning, the loss will look like this. I will have margin between the score for the correct, so this is the correct class, and this is the margin between the score and the others. If the difference come like 0, this means the loss is good. If it's not 0, this means that you need to fine-tune those W to make this loss go to 0. Let's have an example. Assume that we're having some weights, doesn't matter what are the weights, and we have those 3 images. This image produces this score for the cat class, this score for the car class, this score for the frog. First, this one is marked for the cat. So I will find the maximum between 0 and the score of the non-correct minus the correct plus the margin. So this is the correct. I will not touch it. I will subtract the non-correct from those. So 5.2 minus 3.2 plus the margin. This will equal 6.1 minus 3.2, which is 2.9. Then the second one and this one, it will be 0 minus 1.7 minus 3.2 plus 1. This actually will go with this minus 0.7, so it will be minus 3.9. Maximum between those and those is 0. Maximum between those and those is 2.9. So the total loss in this case is 2.9. Why? Because this is bigger than this with some value plus this margin. So this is my loss value. Now I'll do the same thing for the second class. Again, this is a car, this is the correct score. So I will subtract this from this, plus the margin. This from this, plus the margin. For both, it's giving you negative. So I will find the maximum between 0 and this negative. Maximum between 0 and this negative. In both cases, it's 0. So this class or this score is perfect. And if you look to it, it's the maximum among all the other. So it's correct. Look here. Again, where is the correct one? So I will subtract this minus this, plus the margin. This minus this, plus the margin. This will give me 6.3. This will give me 6.6. Again, the maximum will give those scores, so it will give 12.9. So this is a big failure, because the score here is negative, while both others are positive. So this is not a good score. This is a good score. This is so and so. Based on that, I need to change the W's here and recalculate the process again. Now, are those the losses? No. The loss is the average of all of these. So the total loss is the average between those three loss and over the number of samples. So this is the loss that will be used to fine-tune the W's. Okay? Is this technique clear? Again, it's very simple. Yeah, it looks complicated, but it's so simple. Now, is this technique a good one to be used with all classification problem or not? They said so and so. Why? Because as I stated, it's better for the loss function to have one minimum point, right? When this loss function has one minimum point, the answer is no. It doesn't have one minimum point. It has multiple minimum points. So if we try to find, or if we found W which will produce zero loss, will this W be unique? The answer is no. If you multiply this W time 2, it will give you zero loss as well. So there is no unique W for this zero loss. This is not a good thing to use. That's why we are not recommending to using the hang loss or the support vector machine loss for the classification. but it's useful in some application. So put it aside, we will need it at some point. If this is not a good way to find the loss function, is there another good way? He said yes. What is it? Remember when we stated that this is a PDF and the scores that coming from those should be also probability. Does this look like a probability for you? Is this a probability distribution? Does this look like a probability distribution? Think this is a probability distribution? Who does not think this is a probability distribution? How about you on the end? What do you think? Is it a PDF or no? Why? What?
Some of them is not
Some of them are not.
equal to 1.
So if those equal to 1, it will be a PDF? Okay, how about you? Do you think those are PDF or no? I can't hear you. Yes or no? Can you close those computers, please? What are the conditions of the PDF? For any function to be considered as a PDF, it must satisfy 3 conditions. First, the probability or the value must be less than or equal 1. The values here, all of them bigger than 1, and some of them are much lower than 1. So none of them by any chance can be a PDF. The second condition, the probability must be positive. There is no probability value that's negative, not by any chance. Finally, the sum of all the probabilities must equal 1. Means if I sum all of those, I have to be what? 1. The sum of all of those must be 1. Sum of all of those must be 1. Does this satisfy any of those? No. Can I convert it to PDF? They said yes. How? By using some magic function called softmax. This softmax function will convert any score that you have into a probability. How it's working? They said, first, I will calculate the E power the score I'm having here. Why E? Does it have to be E? Does it have to be E power something? The answer is no, it doesn't have to be. It can be 2 power the score, okay? But it needs to be an exponential function, because the exponential function will guarantee what? What is the probability of the exponential function? The exponential function always positive. It can't be negative by any chance. Okay? So E power this will be positive. Power this positive. Even power the negative will be positive. So this way I will guarantee that the scores will be all of them positive. I satisfy the first condition. Now I'm in the second problem, which is what? The sum of all of them must be 1. They are positive right now, but they are too big. Some of them are really too big, bigger than 1. And the sum, by any chance, it will never be 1. So how to solve this? They said I will do normalization, meaning I will subtract each one of them over the sum of all of them. So I'm enforcing them to make a sum of 1. So if I do this step, that's how it will look like. Now it's a probability. So this score, which was not probability by any chance, converted to a probability function. Does it satisfy the 3 conditions? Yes. All of them positive. No negative. The sum of everything is what? 1. Okay? So now I have a probability distribution for the score. My goal now is to compare this to this probability distribution. Remember, as we stated, should be the probability distribution for the data. So I want to compare this to this. 2 probability distribution, I want to compare them to each other. How can I do that? For that purpose, they moved back to the statistics and the information theory. And they found something called KL divergence. KL divergence is a metric used to compare 2 PDF, how close they are to each other. Okay? One metric in this KL divergence is the cross entropy. Because if you look to the KL divergence, it consists of 2 parts. First, the cross entropy between the 2 BDF function and the entropy of this correct one. This one is fixed. So I don't want it, put it aside. So this KL can be converted easily. So this is the fixed one. I don't want it. So the KL will be converted into the cross entropy part. The equation for the cross entropy actually equal minus log the probability of the correct class for this sample. Meaning, this cat belongs to this class. The loss will be minus log this probability. And ignore those. Very simple. That's what we call cross entropy loss. Okay? So this is the second technique or second loss function we can use. And to use this loss function, we need to convert the score into probability. To do this, we will use the softmax function. The softmax will convert the score into probability. And I can use the cross entropy to compare the performance of the 2 functions. If they are equal, in this case, the L will be 0. If they are not equal, this loss function will be high. Okay? Any problem now? So, how many loss function we learned so far? 2 loss function. Can be used for which problem? What is the problem we are solving here? Classification problem. Okay? One of them, which is the Heng loss or the SVM, has a problem, which is it has multiple value for zeros, for this minimum value, which is not good. Will this suffer from the same problem? Let's see. So, minimum value for this loss function. This probability equal 1, which means the value here equal 1, and the others are 0. This means I will be minus log of 1. Log 1 equal what? 0. So the minimum value for this loss function is 0. So yes, I have 0 value, which can occur only if this probability is what? What is it? Yeah, if this probability is 1. If it has any other value other than 1, it will not be 0. So it's unique. What is the maximum value it can have? Be negative. How about this minus? Can it be negative? I think it can be negative. Who think that it can't be negative? Only 2? What are we talking about for 2 hours? Can this loss function be negative? No. Then how can I interpret this minus? The value of y.
Below 1, so 0 to 1, right? Probability.
Exactly. The probability is a fraction. Log of the fraction is what? Is negative. So this log will produce negative value. That's why we added the negative. Okay? So this negative is added to cancel the negative of the log. Okay? So no way the loss function can be negative. Don't think about it. Okay? What if the b is 0? In this case, what is the value of the loss? Meaning the score that I'm receiving here for the cat will be almost 0, or very small, tiny compared to the others. What will be the loss function in this case? What is it? Log 0 is undefined? Are you sure? This is the curve for the log. So log 0 equal what? 1. Minus infinity. Log 0 is minus infinity. So minus infinity equal. So the minimum value is 0, the maximum value is plus infinity. Okay? So this loss function growing up. It's not going down by any chance. Okay? And what helps us in this case, that this is a probability, which means that it's always positive and it's always fraction. And what helps us to produce positive and fraction value is this soft max function. Okay? That's why this soft max function is our close friend in this problem. Okay? We will use it in everything. Even in the ChatGPT, we are using the softmax. So this is our close friend in any classification problem. And by the way, the ChatGPT is a classification problem. That's why we are using this for it. Okay? Okay. How about if all the scores here are equal? what will be the loss in this case? This said, in this case, the loss will be, assuming that the score here is 5, 5, 5. All of them are equal. In this case, if you calculate the softmax for that, you will find that this will equal 1 over 3, 1 over 3, 1 over 3. Right? Because score is similar, after calculating the probability must be also similar. Dividing over 3 part, it will be like this. What is this distribution? Did you see this distribution before? This is uniform distribution. When you have all the classes or all the values have the same probability. Okay? In this case, the log will be, or the loss function will be minus log 1 over C, where C here is the number of classes. So if the number of classes is 10 as an example, it will be log 10. Okay? If the number of classes here is 3, it will be so log 3, which is, I don't know what the value for 3. I have to calculate with the calculator actually. Sorry, I missed something. Okay. Yes. Okay. Now, can you tell me this log of with which base? We know that the logarithm has a base, right? So this logarithm or to which base? Actually, how many bases, how many well-known bases for the logarithm? 2?
E,
Okay, so this logarithm of which base?
E, 3.
Now, if you are saying, see that log 10 is 2.3. This is log 10. If it's log 10, then log 10 will be what? So it should be 1. This means it's not a base 10. Is it a base 2? Look, what is this?
E.
That's why this is should be base. If you change this to 2, then change this to base 2. So whatever the change that you will do here, do it here. So the base here must be similar to the base of the softmax, because this is the function that converted me into probability. Then I have to keep the same base. Okay? Any questions so far? Okay. Now I'm having my loss function. I learned now that I have 2 loss functions for the classification problem. One of them has some troubles, which is the SVM, but as I said, we will need it at some point. The other one is better, which is the cross entropy loss, which where we convert the score into probability. Then we are using cross entropy technique to compare the probabilities between the required Y value and the generated probability from the softmax. And based on that, I can decide which one is which. Again, my goal from all of this is to fine tune or will change those W's. So this is my ultimate goal from the loss function, is to modify the W to make sure that this loss function will be 0 if I can. Okay? There is one small tiny problem. What is this problem? I keep the problem like this and try to find the value of W that give me the 0 L. I'm stuck in a problem in machine learning called overfitting. What does this mean? Assume that you are having this input X. So you have image, which is 2 by 2. All the pixels are 1. Okay? And you have two W's right now. This W and this W. If you calculate the loss based on W1, the loss value will equal what? This time this, this time this, this time this, this time this, and sum, the result will be 1. If you calculate W2, the loss based on the W2, it will be 1/4. That's 1/4. 1/4. 1/4, the result is 1. So both of them give you L of 1. Which one is better? W1 or W2? To solve this problem, they said I need to introduce one extra term to my loss function. I will call it regularization term. This regularization term will be used within the loss function to guarantee that the weights of all the pixels are similar. So if you look to this W, I'm giving higher weight to this pixel. Do I use any of those here? I'm ignoring those 3 pixels. I don't need them. Okay? Here, I'm using 4 of them. Meaning, this one should be better. But how can I add something to the loss function to give high priority to this over this? That's what they call the regularization term. So the regularization term is a term added to the loss function to improve the quality of selecting W and prevent overfitting. You choose this one. In this case, as we said, we are ignoring those 3. We are focusing in this one. If I give you mu X, which look like this, it will give you the same exact classification like this. Sorry, like this. So those 2X will produce the same exact score and will produce the same exact class. Is this correct? This image and this image will produce the same exact score and the same exact class. Is this correct? Doesn't make sense. So this one will overfit or will push the data toward one class against the other, which is not something we want. If you want to visualize this, actually, if you have those points and you want to draw a curve that fits them, overfitting will generate line that will pass over all of them. But those are the training data. If a new data come, which is the testing, you can find that the testing data are here. Does those testing data lie on the same curve? On the other hand, if your curve or your classifier look like this, in this case, you are or a certain distance or the certain error from all of them. So you are still as far from the same range from the testing. So you are in a good margin. So this is considered to be good fit. And this is called overfitting. Okay? So regularization term always prefer simple model, something that not overfits. So this regularization term will help us avoid this overfitting problem. What is the general form of this regularization term? Actually, it can be of many forms. One of them is the L2 norm. Remember the L2 distance? It can be L2 distance, which is the squares of the W's. Some people think about L1 distance, which is the absolute value of the W's. Some people think about something called elastic net, which is mixing between the absolute and the square. In all cases, any of those will guarantee that this term will give us smaller W. Why smaller W? Because we are adding it to the loss function that we are minimizing. So distribute the value over all the W's will make them all smaller, rather than giving bigger value for one and ignore the others. Okay? So now, this regularization term will be the valve, safety valve for our loss. Without the loss, the regularization term, my model can overfit. With the regularization term, my model will be secure against overfit. To balance the relation between the actual loss or data loss and the regularization, we're adding a term called lambda. This lambda and many other parameters that we'll add in the future called hyperparameter. If you hear this word, hyperparameter, this means a parameter that you choose by your own. It's not something that's generated for you. Okay? So this hyperparameter, you choose it as a designer to give priority to one term over the other. What does this mean? If this lambda is big, in this case, the main loss function will focus onto the regularization over the data loss. In this case, the value of W will be too smaller and the model will be very simple. If the lambda is small, in this case, I'm giving higher priority to the data loss. So the value of W will be bigger and the model will be more complicated. So this lambda is my key point as a designer to make the model simple or complicated. At bigger lambda, I'm simplifying the model. Reduce the lambda, the model will be more complicated. Okay? So here are 3 samples. Actually, I don't have it here. Anyway, later I will show you 3 examples for different value of lambda. Okay? Some of them are medium lambda, some of them, actually, let me give it to you very quickly. Yes, actually here. So those are 3 values of lambda. This lambda is very small. So when I'm giving smaller lambda, I'm building a complicated separation between the classes. So the classes, you see, those are the training data. When you receive new data for testing, can be here, which will be misclassified. So this is an overfitting issue. If the lambda is very small, is very big, in this case, I'm giving high priority to the regularization. So see the model is almost line, almost, very simple. The good choice of lambda will give you a moderated one. Not complicated or perfect, and not simple as a linear, in between. Okay? So your goal as a designer, when you are solving the problem, because that's the part that you will do, is to choose the perfect value of lambda to balance between the two parts. Okay? Any questions? Okay. So today I didn't give you a break in the middle because I want to finish early. I think that's better for all of you. Two things I have to mention. First, we have the midterm exam next week. Okay, please be prepared. Include all what we covered until last week, including and the lecture of the principal component analysis that we have online to watch. Okay. Second, by the end of this week, you need to choose the paper that will work for your project. Okay. What are the conditions for this paper? First, the paper must be published in a high reputation conference. You have so many of those high reputation conferences. You have the CVPR, you have the NIPS, you have the ICML, you have the ICLR, so many conferences or journals. If you go to the IEEE proceeding, there are so many journals that handle the computer vision and machine learning AI problems. You can choose anyone with a good reputation. When we talk about the journals, we are talking about the impact factor. So the impact factor must be greater than 1.5, okay, to be considered. If we are talking about the conference, it should be one of the top 10 conferences in the field, okay? Second, the paper must be published at most 2 years ago. Meaning, we are now in 2015, so it can be published 2015, sorry, we are 15. We are 2025, 2024, 2023. No less than that. Okay? Something that published 2 years ago, no more than that. Because as I said, technology in this field is changing rapidly. Okay? So if you get any paper older than that, it may be outdated. That's why you need to work on something up to date. Okay? Before submitting the paper to Canvas, the paper must be approved by myself. So you have to show the paper to me, and I will give you the green light or the red light. Okay? If I said the paper is approved, then you can start working on it. If I said the paper is not approved, don't work on this paper. The paper also must include a demo software, which is available in most, if not all, the papers published in the conferences nowadays. Because the honesty of the publication, the committee of the conference asked any author to include a GitHub link that include the implementation or a sample for his algorithm. Okay, so this code or the GitHub link or the on the university website somehow they provide it on some website. Doesn't matter to it doesn't have to be GitHub, but it's mostly on GitHub. The paper must include the link for the implementation. Okay, so your function or your goal will be read the paper very carefully, understand the function that they are trying to implement, the techniques they are implementing, and repeat the same experiment on new data of your selection. So don't repeat the same experiment of their data. No, you choose a different data and then test the algorithm on your data. Okay? The new data that you can test on can be new data set that has not been tested on or data set from your collection. So you can capture a picture from your cell phone and test over it. You can use it or test it on a new data set. There are so many alternatives. Okay? Anyone have any question about this? Okay. This task should be done by the end of this week. Okay? I think the groups are all set right now, right? Anyone have any problem with the groups?
Midterm pattern like MCQs?
Again, you will see me need multiple choices.
Yeah.
Okay. The midterm will be multiple choice, true or false, multiple selections. So I can give you, for example, 4 or 5 items and tell you select the correct among those. Can be fill the blanks, anything of those. Something that will be automatically graded by the computer. Okay? I will provide the question and the answer in the exam. So the grading will happen automatically. And again, the midterm will take place over lockdown browser. So please make sure that your computer is supporting the lockdown browser. Okay? If you come at the exam day and say, oh, I found that my computer is not supporting lockdown browser, then you'll be in a big trouble. And to test that, I will post a demo quiz on Canvas that just asks you about your name, doing nothing, just to give you the opportunity to install the lockdown browser to your machine. Okay? Any questions? Any problems? Okay, good luck. We take the attendance and you'll be all set to go.